Good afternoon and welcome to today's joint astronomical colloquium. It is a special pleasure to welcome Jos Bland-Hawthorn from the University of Sydney, who will be speaking to us about the very center of our Milky Way, about the recent Seyfert history of our galaxy. Before we start with the talk, let me quickly introduce the speaker. He is British. He did his PhD at Greenwich Observatory and the University of Sussex. Then he moved to Hawaii, to a very different island, I guess a bit more tropical than the British Isles. He stayed there for, I think, altogether 3 years, and then he went to Rice University to take a tenured professorship there. After that, he moved to Australia, to Sydney, where he has been since. And he has been extremely active in the Australian community. He has won many prizes. I just mentioned a few. There is, for instance, the Federation Fellowship that he got in 2007. He got a laureate fellowship from the Australian Research Council in 2014, which is one of the most prestigious research prizes in Australia. He will next year be Miller Fellow at the University of California at Berkeley, and there are many other things in between on the list of prizes and honors that he has. He is the director of the Institute of Astronomy in Sydney. He is very proud. He told me that Australia is now a partner in ESO, and he's working very strongly to make it a full membership. And I think with that, now that the last people are coming in, let's get to the science. Let's welcome Jos and learn about the recent Seyfert history of our galaxy.
Thanks a lot for that. You didn't even mention my greatest claim to fame, which was several years ago. I was described as the Hans Volta of Australian astronomy. I thought you were honestly thought it was the Hans Volta of Australian astronomy. I think that's because of our zest for life.
That's 10 years over that.
So anyway, I was very proud to be referred to in such an illustrious way. And here I am at the Metallicity, where Hans Volta lives. Alright, so recent history of the galaxy. There is a developing paradigm which is quite shocking if you get to the end of this talk and you're still awake. If you literally have to check yourself at the end of this talk and say, is this all for real, or is it all just rubbish? I would say the case for it is overwhelming, but of course it's all in the details. Can you believe the details of what we're claiming? But the galaxy in the very recent past, when cavemen and cavewomen walked the Earth, was once a very, very powerful, safer galaxy. Let's see how this goes. Well, in 2010, if you were reading the NASA press release, you would be forgiven for believing that the galactic wind was discovered by NASA, by Fermi, by this wonderful result of the Gammaray bubbles. This, by the way, for theorists in the audience, is an artistic representation of the not the activator, just in case, just to be sure, there's a lot of theorists here. In actual fact, the bubbles, as in bubbles observed large-scale wind, people have been saying there might be a rain for decades. One of your colleagues here, Dr. Vogt, was saying to you that he was one of many that have made this claim. I think Lockman in 84 and Bregman in 88. Many people thought there should be some kind of a wind. But the first time it was actually seen was my paper in 2000 and, oh my gosh, why is it not displaying white? Is there a reason for that? I don't know. I've not seen that before. But yeah, it's giving me. This is very unusual. I've never seen this. How bizarre. Since half of my slides have a white background, this would not be very good. Come on. Should we say one slide? Huh? Yeah, but I have lots of white backgrounds. So Huh? Exporting PDF gets rid of all the things that overlay and all the rest of it. Oh my gosh. All right, let's try again. I wonder why it's doing that. All right, if we get past this, it will go well. Let's hope it does. Try again. I have no idea. Here we go. So in actual fact, 2003, there's a paper by myself and Martin Cohen, the large-scale bipolar wind in the Galactic Centre. And in our very paper, 2003, we had this figure. If you look to the right, you see ROSAT data. It's actually a German discovery, not an American discovery. ROSAT data, 1.5 keV. The important point there is I was arguing that it had to be further away because you don't see it in the soft X-rays. And ROSAT capacities, like visible capacities, will put the bubbles further away. I'll tell you more about that in a moment. But as you see, this looks an awful lot like the bubbles observed in the Fermi data. To be honest, for some time they were very slow to recognize any firework, but they got much better at being open about this, I felt, in 2014 when they received, quite frankly, the Rossi Prize for their work, and they did actually acknowledge this past paper. But what I really want to talk about is the issue of power and timescale, which is a very nice story. And one of the papers on that sets this in motion is my paper in 2013, Fossil Imprint of a Powerful Flare at the Galactic Centre along the Magellanic Stream. In actual fact, some people have referred to this now as the Magellanic Screen, because I'm using the stream as a screen of all the stuff coming out from the Galactic Centre. And it's that work, I think, which has helped to really tie down energetics and timescales. But to see this story, I have to show you a lot of other work besides. Here's an overview of the talk. Galactic Centre wind, age in a starburst. When did it all happen? The stream mystery. As you'll see, there's a mystery coming up. I will then show you some models, the first of its kind, at least in the galaxy domain, time-dependent for ionization, new models developed with Ralph Sutherland, new results from HST COS, UV spectroscopy in particular, and then finally, and interestingly, consequences. How does all these new results tie in with all the other observations we know about? And sometimes you go back and revisit data you've always known about but forgot about and see it in a new light. And I will end with comments about the developing paradigm of what we think we now know about Seyfert galaxies. This is work from many fields. First of all, the wind. So 2003 was my work with Martin Cohen, and the energetics we came up with was about 1055 ergs. The referee didn't like that. The referee said this is just to do with the local bubble. There's a local bubble, there's also the North Polar Spur, and for many years people argued this was all very, very local. And the referee, interestingly, wisely said, your case for having this further away than local is not compelling. What is the evidence? So I had to go off and do more work, and the two arguments we came up with, which the referee seemed to, well, not abjure, accept, were the fact that the polar structure is not seen into the center in soft X-rays, only in hard, as you'll see later. And secondly, OB association blowouts. If you thought it was somewhere on a spiral arm between us and the Galactic Centre, which is 8.2 kiloparsecs away, you don't ever see hard X-ray, gamma-ray structures in OB association. In lots of galaxies, this idea of like lotus leaves, NGC 3079 is an example, where you have inner blowout and sort of outer blowout structures, and also what looks like a disk-wide wind. So here's the soft X-rays. You don't see that beautiful hourglass structure into the center at all. You see a real mess in soft X-rays. Oh, I thought it was more powerful before, wasn't it? What am I doing wrong? Here's the blow-up on plus or minus 20 degrees, and right in the center, you blow up again. There's this beautiful mid-infrared structure, the first mid-infrared galactic wind detection ever, and it overlays beautifully with Sufue and Handa's work in the 1980s, where they saw that in radio continuum, as we show. The last line of my abstract is energetic winds may be far more common than we think, but very difficult to detect, because if we see it here and nowhere else, presumably these things are everywhere. They're more common than we think, but just very hard to see. We always see the powerful winds, the sort of the top end of it all, like M82 and so on. Now, 2010 was an exciting year, no question. Nobody anticipated, not even my paper. I had thought there would be other diagnostics like UV absorption line spectroscopy, which we did. I did never perceive, nor did anybody else, that these winds could generate gamma ray emission. And here are 6 slices in energy, three slices in energy, 1.3, 3 to 10, and 10 to 500 GeV. It's difficult work. You have to subtract off a background from the galaxy itself. You have to use dust and CO and H1 to compute what the background gamma ray emission will be. Molecular clouds are the brightest thing on the galactic sky. Molecular clouds, because of things like pion decay, they're bright. You see bright sort of blobby clouds in gamma ray emission because of these pion decays. So you have to remove that background. And I know that they struggled to get their work accepted early on at various meetings. I'd received emails from people saying, do you believe any of this stuff? And for me, it was fairly obvious, fairly early on, that what they were seeing were bipolar structures from the Galactic Centre. So this is very nice work by Sue, Slatcher, and Fink Biner. And there have been papers since. They were awarded the Rossi Prize 2014 for the discovery in gamma rays of the unanticipated Fermi bubbles. I think that's a correct statement. So if you zoom in to that and start doing collages and overlays, you'll see now in an 8-off projection that what I found was pretty much the same as what they found, and it fills in the base of their bubbles really very well indeed, even in the details. As you see here, I've actually sort of translated that up here so you can see more clearly what's being overlaid. So these really are the same structures on 10 kiloparsec scales. 2 things to be aware of. One is it's rather smooth, the gamma ray bubbles. They also have rather sharp edges. Wherever you look, there really is a very sharp domain like that at the edge of that bubble. And furthermore, the spectrum is very hard in gamma rays, and it could even go a bit further than 100 GeV on towards a TeV, I don't know, but somewhere beyond that, which Felix knows all about. So possible origins, before we get to the good stuff. First is leptonic. Cosmic ray electrons, inverse Compton scattering off the CMB and the interstellar radiation field to produce gamma rays. And here are some of the key references that make this point. There are a bunch of papers that say this. And here you have essentially a fast-moving wind. In my annual reviews, 2005, with Veyer and Cecil, we give many examples of galactic winds. These are always moving fast, 10,000 kilometers per second. They're very, very hot. You never observe the wind. In fact, all previous claims seem to have gone away. What you observe is what's being pushed or entrained. The cool filaments, which are moving at, say, 1,000 kilometers per second or slower. Be aware of that. That's always difficult to interpret. You see this stuff being dragged along with these winds. That's not the wind itself. And that's basically the argument behind these wind-driven solutions based on cosmic ray electrons. I'm sorry?
Why don't we see those?
We do. We do. Already the projections are hundreds of kilometers per second. Yeah, easily. So yeah, the HST cost results are hundreds of kilometers per second deprojected, and the X-rays, and we'll get to that. There's not a problem with that at all. So the next one is hadronic, which was a project, it's basically a series of papers that Rowland Crocker has been promoting, that you have cosmic ray protons colliding with thermal nuclei producing neutral pions, and these degrade to gamma rays. The timescales there, however, are very long because you need star formation to generate these cosmic rays, to generate these cosmic ray protons to fuel these bubbles. And now you get to much longer timescales because in the Galactic Centre, the star formation rates are low, not high, as I'll show you. And these papers, they began with something like 9 gigayears, and they've come down to 300 million years, and sort of the timescales for these papers have come down, 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 but I feel that these timescales are much too long, as I'll get to. The last one is what Rowland calls gin and tonic, dark matter annihilation. There are people who like to propose this, promote this, well-cited papers. The one by Finkbeiner, one which is published, one which is not published, has a lot of citations because there are a lot of frustrated particle physicists, astroparticle physicists, that like the notion of there being dark matter annihilation observable at the Galactic Centre. So let me finish by saying on this slide that gamma ray bubbles are sharp-edged. They seem to be trapped particles, possibly turbulent field. It's advecting in a magnetized plasma. expanding thermal bubbles. This is the sort of idea that you see in many papers which have emerged since. And I would say that there is really not a strong case for the hadronic process at the present time. And I'll show the models of that towards the end. Further evidence for the wind, old and new. Have we known about the wind before and failed to recognize it? Possibly yes. This is the H1 map of the Galactic Centre region. The red dots are spaced by 1 kiloparsec. And Lockman and McClure-Griffiths, 2016, presented this. In actual fact, Jay Lockman has been saying since 1984 that there's a paucity, missing gas over the Galactic Centre. But as I pointed out to him years ago, and I still point out to them, this cannot be confirming evidence of a wind, because after all, ionization can do that for you as well. So here's a full ATOF composite of those 3 observations. Here's the H1 to scale in an ATOF projection. Here's the ROSAT 1.5 keV in an ATOF projection, and here the combination of all 3 of those bands. So there are all sorts of different kinds of observations, confirmations of this wind. The latest, there are now a series of papers to do with the Hubble Space Telescope, looking at background quasars, also background halo stars, right in the Galactic Centre, some in front of the bubbles, some behind the bubbles. Well, I think we're up to something like 70 sources all told. No, I think some of those along the stream, actually. But there's been something like 70 quasars observed by this team, and we're up to paper number 5 or 6 or something, if you go back to Fox 2013. And these papers are very interesting because they reveal all sorts of interesting absorption lines along the line of sight. Now, to go to your question about do you see 1,000, well, you see that in lots of outflow galaxies. Specifically in our galaxy, you have the problem of deprojection. So when you see something like this, here you have one at plus 250, here you've got minus 250, and the components are other velocities. Here's minus 200, and there are components which are slightly higher in velocity. But we're seeing through something which is moving transverse to our sight line. So now you have to worry about how it's actually moving in 3-dimensional space, and you could easily model that in terms of much, much faster filaments, depending on how you project those filaments. And that's pretty much what we do in the annual reviews for external starburst and AGN-driven WIM galaxies. Here are 3 of the...
Show me at least one of these where you're looking along the motion and it's moving in 1,000.
But you're in the galactic plane.
I understand the projection effects. I'm just saying there is a probability that I happen to be along that motion. So at least one spectrum to show
Well, you're welcome to download the data and look through an awful lot of absorption lines and measure for yourself whether these...
never get up to more than 250.
That's in projection.
I understand it, but I mean, if I'm looking at a wind in projection, occasionally I'm going to see 600.
I don't think your case stands up at all. Whenever you model these bubbles and project it into what we see as we do in the paper, you infer a much higher velocity. In fact, the X-ray modeling of the emission would put you at 500 and nothing less. Maybe, in fact, even higher possibly. As I'll show you in a moment. We'll get to the X-ray emission emissivity. Actually, it's coming up quite soon. So the point here is that we have nice control fields where you see stuff in front and you see stuff behind the bubbles. There are different kinds of tracers through the bubbles. This is really interesting because it's now with 07 and 08 emission observed by XMMNewton and the Suzaku X-ray satellites. And when you look at these across the sky, you find these regions out near the bubbles which are brighter than the other regions across the sky. And I will show you in about 10 slides what they infer from modeling these data as a shock, as stuff being swept up in a shock. So, AGN or starburst. It really depends on whether you think you've got something which you can associate with many other things on external galaxies, or whether you want something exotic, which is truly ancient, that takes you back to the beginning of history. So, star formation rates in the Galactic Centre, which we know uniquely from resolved stars, unlike any other galaxy, big galaxy, you end up with something like 0.1 solar masses per year within a few hundred parsecs. So any kind of star formation-driven anything is pretty wimpy by galactic scales. And I would ask you basically to compare that to our annual reviews 2005. But I would definitely agree that something violent has happened in the Galactic Centre on much longer timescales if you look at my annual reviews with Ortman Gerhardt, which came out at the end of last year, we show the baryon to dark matter profile as a function of radius, and sure enough, baryons dominate pretty much everywhere out to the solar circle. Dark matter picks up much further out. NFW profiles have incredible cusps in dark matter all the way to the center, and the way that we understand that, people like Pons and Governato gave beautiful pumping mechanisms to do with star formation rates when the galaxy was very small, pumping out baryons which move the dark matter around and basically wipe out the cusp. You might say that in a sort of conventional way, that's one of the best evidence we have for very violent past activity, if you accept that NFW profiles should have existed otherwise, but for the baryons. Now, in the Galactic Centre, the problem with AGN versus starbursts, as always, with Seyfert 2s especially, is that half of these have something like starburst nuclei. Star formation seems to go together hand in hand, often with AGN activity. I would say, however, that all the stuff coming up, the starburst can never supply anything like the amount of UV that we need. That's down by a factor of 200 over an AGN description. There's something very exciting going on in the Galactic Centre, lots of flickering activity. If I blow up this region and show you this, there have been people showing there's been something like Thomson scattering of molecular gas, superluminal FEK echoes. Sunyaev wrote the first very nice paper on this back in '93. Kayama, Murakami, Terrier, Ponti, and a host of others have shown that you have flickering fluorescent activity in the Galactic Centre, and individual regions of the molecular gas are variable. And these are very powerful detections, 13 sigma. We're not on about 1, 2 sigma stuff. Also, in X-rays and also in infrared, you'll find there's all sorts of flickering behavior. It's 10 to the minus 8 Eddington is the quiescent state, but occasionally, in the last few years, there are events which are 1,000 times the quiescent background, so 10 to the minus 5 Eddington, but always on very short timescales. For me, having worked in this field for a very long time, I'm not remotely concerned about the idea of the AGN once having been more powerful and having flickering behavior. And there are many spirals, many. If you push hard, like they do in Australia in the radio surveys, if you push hard on these things, you very often find, I don't mean 100%, I mean like 10%, you can often find evidence for some kind of mass ejection from the centers of these disks. Here are 30 or so examples. Here's one beautiful example from Bill Keel of an L-star galaxy blowing off some kind of biconic radio structure. This doesn't have to be any different from the Fermi bubbles. Here are other examples. This is Adonis, a nice group. Most galaxies, like M31 Milky Way, are in loose groups of 1 or 2 spirals. That dominates the local universe. And this source in particular has a beautiful ejection, as shown up here. Another example comes from the Gammaray survey. This is work that Richard Tufts is involved in. 2 spirals, very much like the local group. One of these also has a Seyfert nucleus. Here's another recent one, also from that survey, with a beautiful radio jet from Wang and colleagues. So the idea, I know it doesn't gel with the notion of powerful, well-collimated dynamo jets in ellipticals, but spirals have them as well, just a much lower emissivity and lower energetics. What I want to get to is, when did all this happen? If you go down the path of saying it's something to do with the AGN, which I think is the only tenable model that we have, when did it happen? Well, in my paper, we'd begun writing our annual reviews, and I'd known for years from prior work with Sylvain Veilleur and Gerald Cecil that everything we ever saw on 10 kiloparsec scales was always on timescales of 10 million years or less. And the energetics of these winds, AGN or starbursts, were always relatively low as far as we could infer. However, it does depend on what you see moving. If you're looking at molecular gas, the energetics goes way up. If it's just ionized gas, the energetics can be quite low because of the mass, the momentum that you're trying to infer from these filaments. So on timescale, the Su et al. Paper said, well, maybe timescale of about 10 million years seems appropriate, but they upped the energetics by a factor of 10 to 100. Which is very interesting, given back before my paper, people were saying it couldn't be much more than 10 to the 52 ergs. There's an interesting paper which really put the cat amongst the pigeons by Rowland and Felix. Basically, I felt a couple of very fine physicists looking for an interesting problem. I got onto Rowland's case, being a fellow Australian, saying you really should read the literature about what we know about winds before you write these sorts of papers. But anyway, it stuck. And he had this idea that this was like a multi-billion-year-old reservoir, maybe as much, he says here, greater than 8 gigayears, say 9 gigayears in age. It's an interesting notion that you have this sort of fossil cavity building up these cosmic ray protons, which at some point explodes. But anyway, his papers since then have come down from 3 to 1 gigayear down to, I think, 300 million years. I think there's a paper he's got coming out where it's 60 million years. So I think he's sort of moving more in line with the picture that's coming out from many other bits of work. So on to the mystery of the stream, or the screen, if you want to call it that. Here's a picture of the stream. And what I want to show you are some results along that stream. This is the H1 being shown in pink. The leading arms from Mary Putman's thesis are down here. This is the trailing arm or stream. Here's the LMC and the SMC, and it goes over the top. And this is now Magellanic coordinates, often quoted like this, 360, 330, 300. So the SGP is at 300, but sometimes with negative numbers, C60 from 0, minus 30, minus 60, and so on. So it's quoted both ways, depending on whose work you're reading. If I now look at the H1 in that stream from 310 out to 260, 250, the red circles show you wherever you get an H alpha detection, and the blue circles where there's a non-detection. Interestingly, when you take the H1 and the H alpha, they match 1 for 1. So this really is the same component which is being ionized. The lines are also at the resolution of the instrument, and they are unresolved, which means you're seeing static photonization from some source. If you look at the signal now along that stream from 340 to 260, the measurements are very faint. These are millirayleigh. Now a millirayleigh, 330 millirayleighs, is 2 to the minus 18 in CGS units. You might recognize these units much better. Mission measure of 1, essentially, 10 to the 4K gas. So that would be a mission measure of 1 would be here. So these are very faint detections, like your Keck spectra or VLT spectra after several hours looking at your faint night skylines. The reason you can get to these amazingly faint levels is using the Fabry-Perot trick of azimuthal binning, 40 angstroms over 4 million pixels, so many pixels per angstrom. So this is intrinsically faint, but very bright for what's expected from the galaxy. My original model for the galactic radiation field had this down by a factor of 2, but Chris McKee convinced me that you have to also factor in all the old X-ray bubbles from star formation in the galaxy which generate EUV emission. So I've doubled that to accommodate Chris McKee's work with colleagues. So what we're seeing here is way in excess of what the galaxy can produce from standard sources of UV radiation. So this is what it looks like when you take that box away. There are even a couple of clouds where the levels are much higher, alarmingly high. And these are data taken from Mary Putman's thesis, work with me, the WAM survey, and also group in the US. So that's the model for the galactic radiation field. Red is soft, blue is hard, basically UV and higher. And what you get is that the surface brightness of H alpha in millirayleighs for the galactic radiation field would be 21 times a fudge factor of 2. That's 40 millirayleighs at a distance of 55 kiloparsecs. The stream now is not thought to be at that distance by anyone in the field. Everybody, like, for example, Guttina Besler at Harvard, Lars Hörnquist, everybody puts the stream much further out because the halo is much less massive than we thought. LMC SMC is known to be moving much faster, and the bound orbits put the stream much, much further out, maybe even 150 kiloparsecs, but I would say 75 to 100 to be safe. So in fact, this level would be even lower if you were to put the stream at what's considered to be the correct distance. So a model which comes to mind is something like ionization, ionizing radiation from a Seyfert nucleus. Here's an example which extends to about 35 kiloparsecs in NGC 5252. This is not unlike the mass of the galaxy, and it has this beautiful Seyfert radiation field blasting off in an ionization cone. Interestingly, I saw a paper by Kramer and Veilleur where they saw an ionization cone going to 90 kiloparsecs in the case of one of their nearby Seyfert galaxies. So the simple model to explore looks something like this. Let's imagine that we have these clouds. These names of clouds come from the original Matheson paper. Here's the LMC, and basically you've got some kind of radiation and some kind of cone going off at some axis, which is not that well defined. A question which comes up is, if we see it on the stream, why don't we see it on the high velocity clouds? Well, Josh Peake answered that question nicely with his collage of HVCs. This is radius, this is height above the galactic plane, and in fact the HVCs, even though they seem to cover the sky, they all sit low in terms of galactic latitude and longitude distribution, puts them all in here. They're not in the main cone above and below the poles, which of course is consistent with what Jay Lockman has been telling us. So, to the supermassive black hole, now very well measured in terms of mass. Its basically release energy would be something as large as 1060 ergs over the course of its lifetime to have formed. And today, the Eddington luminosity would be something like 0.2 solar masses per year, which is not dissimilar from the star formation rate averaged over the inner 300 parsec radius in the Galactic Centre. So now I use a basic, straightforward model. This is not the entire topic of my talk, this is just one aspect of my talk. And what you get here, in the flash, not on average, in the flash, is 825 millireles. This is unbeamed, B of 1, escape of about 10%, Eddington luminosity of 10%, not 100, escape fraction of order 100%, that comes from Mulcahy's work on ionization cones, that you always seem to see the release as if something else like a wind or starburst wind or any other wind has blown the gas away, as we see in Lockman's work, and then the distance to the power of -2. And then in the case of our modeling, just to be consistent with Seyfert's which have been observed and across the energy range, we've basically got a big blue bump and a slope, and that big blue bump actually gives you a little bit of a boost, factor of 2 or 3, in the UV photon number count. So one thing you learn when you do these time-dependent ionization calculations is you have to worry about the metallicity. It's no longer solar, you're a 10th solar, you're on the stream. And this comes from, again, from HST Koss work by Fox and colleagues, 2014. Everywhere along the stream, it's a 10th solar with amazingly low scatter, except when you get near the LMC and the SMC, it goes up by a factor of 2 or so. But along the stream, it really is at this value. So when you put that low metallicity in, cooling counts for less than recombination. Recombination is really quite fast, but they play off each other, and you have to worry now about the details when you interpret your diagnostics. So that flash is followed by fading recombination emission. So what we're seeing today along the stream in my model is something which is fading from a glorious past. It probably isn't, we're not catching it in the flash. If anything, we're catching it after the flash. In the flash, by the way, you start to generate things like O3 emission, helium-2. Those of you who know about ionization parameters will know why. As you get the photon flux compared to the gas density fraction, then you get this much higher ionization diagnostics from Saar's equation. So basically, what we have here is, in the flash, you would have much harder diagnostics than we possibly observe in emission. So we're in the fading regime when H alpha and H beta become important. In fact, the ratio also becomes important. So if the streams are 55 kiloparsecs, you have quite a lot of wiggle room. But if the streams are 100 kiloparsecs, you don't have as much wiggle room to explain the background emission signal. And that's for an Eddington of 1. If you want more wiggle room, I could have increased this by another factor of 10 or 3. So what you have then are the same data points in longitude, Magellanic longitude, and what you're saying now is it jumps onto the diagram either here or here, and then fades down to the current background, which is a different interpretation from just saying it's statically ionized by an impulse. It's something which has been fading since a past event. Now, so what other evidence do we have that the stream is being ionized by something rather interesting, something from long distance? So this is new evidence from, again, from that same collaboration of HST Koss observations. They have many sight lines along the stream. In fact, they have so many, they were able to bin them up into bins of Magellanic longitude. There's a region here which is missing. There's a region in here which is missing. This region here is right by the LMC And something was known about that already because of the very hard ionization diagnostics that you get from all the active, like supernovae and individual events in the LMC. There's a lot of very interesting diagnostics known about the diffuse gas around it. But then you end up, I should be more clear. The red is high ionization based on the S3, S4 to S2 to S3. Green is low, and H1 content is shown in, the neutral fraction, sorry, is shown in blue. And what you see is hard ionization at the LMC and hard ionization distributed around the SGP. And more work is now going into to basically look further out this way and this way to see if it really is confined to a cone somewhere around the SGP. So when did this ionizing event happen? When did such hard ionizing radiation hit the stream and thereby cause the fading of the recombination emission? And what I really want is something which is independent of the wind estimates. The wind estimates now come from models of the Fermi bubbles, models of the X-ray emission, which I'm about to show you from Bregman and Miller. And I want something which is independent of their timescale. And there's also timescales for young stars formed in the Galactic Centre. There are different timescales. The question is there a narrative? Do they go together? So current models are unable to tell us if disk-driven winds and UV bursts can occur together or whether they're different. I've asked this question of numerous colleagues like Roger Blandford, Ramesh Narayan. I spoke at Stanford, I spoke at Harvard. You go and ask these people who do this for a living, and they're very uncertain about just when an accretion disk feeds, generates some kind of a wind flow, and when the radiation goes off. How do those work together? Is one opaque to the other? Does one interrupt the other? It's very hard to know for sure how these GER-MHD models work. And in fact, Ramesh Narayan promised me some predictions on this, and they never arrived, I presume because too busy or there's too much else going on at the moment with the code. It's a very complex, large code that this group has developed. So what about that timescale? So consider a flare that took place at some time in the past, T0, for a burst time of TB. Here are the timescales you have to worry about. First of all, you have to worry about the radiation propagating out to the stream, and then you have to worry about the recombination signal coming back to you. The second thing you have to worry about is the march of the ionization front into the stream. You ionize the gas, you know, basically the ionization parameter couples to that march, the speed of that propagation into the gas. If it's a high ionization parameter, it marches faster in. So that's important. How far can you go into the gas to give you the emissivity that you want? That looks like 4 10 to the 3, phi 6, which is the number photons 10 to the power of 6, in units of 10 to the power of 6 per cm squared per second. And you need something like 4,000 years to get enough into the stream. The double crossing time out to 55 kiloparsecs and back, that's more like 200,000 years. If you put it 100 kiloparsecs, it's more like 400,000 years. Then you have to worry about the recombination time. That now depends on density. These are all geometric. This one now is more about density. 100,000 years at a density of 1. And all that have to come in together. If you put all that together, what you end up with is a minimum energy to make the ionization happen and be observable is 10 to the 56 ergs, and the minimum mass of gas which powered the accretion disk to generate this event at 10% Eddington for the duration is something like 4,000 times the mass of the sun. Those numbers seem fairly reasonable. Now if you put the stream at 55 kiloparsecs or 100 kiloparsecs, that T0 has different answers. You get 500,000, half a million years at a density of 1, 0.3, 0.1, and down here 1, 0.3, and 1. And basically, they're all saying you're somewhere between 800,000 years to 3 million years, assuming you have the correct column. It can't be too long into the gas, otherwise you run out of gas. So you get ionization timescales of a few million years. 1 to 3 million years, although, of course, if you do all this marginalization thing, you could definitely get longer and shorter timescales. The burst timescale I have no constraint on. I can't tell you how long it lasted because of the playoff of density and ionization along the stream. All I can say is I need at least 4,000 years for it to march far enough into the gas to give me the emissivity. So shock modeling of the bubbles done by Miller and Bregman, they claim very accurate post-shock speed for the X-ray emission. They do a better job than I did in 2003, frankly, because what I had forgotten to do which of course is what I could have learned if I'd done my work properly from the Fermi crowd as well, is to remove the background before you claim what's in the shell itself. I didn't do that. I took everything gratis as you see it on the sky. They remove the background and then say what's in the shell. Pretty sort of analogous to what the Fermi crowd did for the X-ray, the gamma-ray bubbles. And they end up with a time scale for the bubbles of about 4.3, which seems rather accurate, but let's go with it, plus or minus 1 million years. And the post-shock speed is a whopping 500, I think it's 480 kilometers per second. I should have put that on the up here. But it's a whopping number, post-shock velocity, to get this signal. So maybe this is to answer your question about what evidence do we have, if you believe the X-ray emission alone, forget all the other diagnostics, this may be the best number that we have so far. Have a look at that paper and see what you think. So Guo and Matthews wrote a paper. I was at this workshop that Roger Blandford organized discussing the Fermi bubbles, and they had a timescale in terms of an AGN jet of 1 to 3 million years, which lasted between 0.1 and 0.5 million years. I can't talk in these terms, they can. And they said an energetic could be as low as my number, but they thought possibly higher to really make things make sense. And in fact, there are dozens of independent groups that have got these AGN-powered models, leptonic models, and in fact, there seems to be one every month coming out from somebody. It's just remarkable how many papers are being written. Here's the Guo and Matthews 2012 paper. This is the cosmic ray leptonic model, and this is 1 million years. This is 2 million years. They have this X-ray emission as the shock front. They have the gamma ray bubbles where the inverse Compton scattering is going on. In Guo et al. 2012, they wash out this frog-like structure with diffusion. Here you see a lot of structure because they didn't include diffusion. Very recently, Narayanan and Slatia have written a paper and make the point, if you believe their use of this sort of background subtraction, that the inverse Compton scattering, the model points are dots with error bars. The data for the different latitudes, that's 10 to 15, 15, 20, 20, 25, 25, 30, 30, 35. Basically what they're saying is they feel that up to 100 GeV, and depends really what you think is, actually it's a bit more than that, isn't it? But I don't know actually what's going on. We had a good chat today with Felix. It's not clear what's going on beyond 100 GeV anyway. But they're feeling in their paper, which came out just a few months ago, there's not much wiggle room for any kind of pion decay. Although as Felix was as assuring me that what they really must do much more carefully is look at the details of what they're claiming in their model. It sort of hides a lot of sins. So do we need a jet to prove the existence of any kind of AGN-driven model? Everybody I've spoken to who are experts in this field say they're not moved by the currents of a jet or otherwise. So, I mean, Jerry Ostrico and I spoke at Columbia on a related topic than this, but related enough that he mentioned that in this regime, if you go with high FE, Eddington luminosity fraction, in fact, you are more likely to have these winds. And there are numerous papers that show, even with the high-power jets, you only have to hit one fragment, like an AGB shell, dust shell, and this thing diffracts and spews its stuff all over the place. In fact, it's rather miraculous that these thin pencil beam jets get out in observations, because you just see from simulations that they should never get out. It's really quite remarkable they get out at all. So is there evidence for a jet? I don't think we need one, but let's have a look. One of the most interesting claims is this one, but I don't think you'd believe it. It's like 1 sigma contours here and here. This is the VLBA observation, Baron-Backer 98. There are similar claims, very weak, fuzzy claims by other authors. I don't think the case is convincing at all for the existence of any kind of jet. So what can we learn about the galaxy? I fear that I'm getting close to finishing, which is fine. Is that right? I didn't get a timekeeper. Yeah, 5 o'clock, so we finish at 5 or 10? I'll get to within 10 easily. So what can we learn about the galaxy from these new observations? Well, I've been slow to realize, what others have known for a while, is there's a lot of work going on about the hot young stars in these rather bizarre annually around the Galactic Centre on parsec scales. Elliptic streams, someone calls them. Some even talk about retrograde streams. And I don't know enough about this literature other than to quote the numbers which are being put out in these papers. This ring of O stars seems to have been born between 4 and 8 million years ago. Everyone seems to agree there's some kind of annular hole in the center, which is interesting. And the last paper I saw last month said that there were 177 O stars measured and counting. And some appear to be going in a retrograde orbit. It's very bizarre, very interesting. Lots of timescales coming in at the million-year level. The Fermi bubbles for the AGN-driven, jet-driven work, these are arguing for timescales between 2 and 6 million years, although you will find some models that push down to 1 and others that push up to 8 million years. With a burst time somewhere, I'm averaging now over about 15 papers, somewhere between 0.3 and 1 million years. And one wonders if there's something about the central hole here, which means that when this ring of, you've got to understand, this is a remarkable result because the galactic bulge, some of you must know Melissa Ness. I think she was here in Heidelberg for a while, was she not? Melissa. Yeah. So Melissa, are you here, Melissa? Probably not. No. So Melissa did a fantastic job looking at 20-odd thousand stars in the Galactic Centre. The Galactic Centre is really old. You know, every star, when you do work on the Galactic Centre, it's a very, very ancient population. Like almost entirely, the mass is ancient. And then you have this very young ring of stars. What the heck are they doing there? Very interesting question. So there are lots of papers on how to feed a black hole like this. Here's just one of them. I like this work because it just seems to, you know, describe so much of what's going on. And if you believe it, I think Ralph would be far better qualified than me to say whether he believes this work. But Lucas, Burnell, Davies, and Rice had this lovely paper to read through at least. And what they're saying is a prolate gas cloud perpendicular to the orbit plane. And notice the dimension of that cloud is of order the impact parameter around the black hole. And what they say is if you make that cloud turbulent and clumpy, as that gas does its Bondi-Hoyle thing of washing around like Wardle, I think, was it Yousafzadeh and Wardle had this paper. The stuff just washes around that sort of Bondi-Hoyle thing. If it's clumpy and turbulent, you don't lose all the angular momentum. Otherwise you do. Otherwise it just shocks and falls in. So if you make it clumpy and turbulent and filamentary, as it goes round, you lose some of the angular momentum, but not all of it. I know we tend to think of gas as just sticking, but not if you make it clumpy. And what they then end up with is elliptic streams of stars, and I believe in some models now they're able to get retrograde streams of stars as well. It just depends on how the gas falls in and how, you know, so this stochastic effect of what misses. This group, I guess like other groups like Ralph's, talk in terms of sink particles, and they have their own accretion scenarios for what mass a star is when it sinks, and they end up with a mass function where they claim their model has an IMF which is tilted towards high mass stars, sort of 10 and higher, thus to explain the O star, the 177 O stars. So it's a very interesting work, and I am not qualified to say how realistic this is in the context of work that's being done elsewhere in the world. People in this field would know better. So anyway, the mass of gas they need is about 20,000. So that's not so far off. Remember, my minimum requirement for some of the gas was about 4,000 to give me my minimum burst energy. Now, what's really interesting is the amount of work going on the issue of what an accretion disk actually is. There's a distinction between accretion disks around ellipticals and massive systems, massive black holes, and accretion disks in the low mass limit. I forgot now to add a video. I wish I should have shown you a video of how these evolve. Because it gets to the issue, as people have asked me, could this radiation field blast the solar system? Well, actually the answer is yes, when you're at the low mass limit of black holes. Because these accretion disks are unstable in toto. They come together, they fall apart. They come together, they fall apart. They're floppy things. And also, what happens in the low mass limit is they flicker like crazy. So here's one model, Novak, Ostreicher, and Ciotti. I was able to get these models from them before Novak went into Google or something, some well-paying career. And this is Eddington from 10 to the minus 8, which is where we're at, to Eddington of 1. And what you've got is this flickering output from this accretion disk on timescales of billions of years. If you zoom in here, it's sort of fractal all the way down. Same thing in here, more like flicker noise. If you zoom into there, you get this. If you zoom into this region of 100 million years, you get that. And what they did was take the power spectrum, and here's the power spectrum, And this is 1 million years. This is, where are we going here? That's, yeah, so what's one of the frequencies. So that's, yeah, so I think this is million-year timescale. Is that right? Am I reading this correctly? Yeah, so longer timescales are, yeah, so on longer timescales, you have a flat response. That's given to you by the CDM hierarchy. And then what you have is this 1/f noise on the short timescale to do with the flickering response of these unstable and floppy accretion disks. So I then was so struck by this, I had to go and find another model which would do this. There was only one other model I could find that would do it, and that was one by...
Right, this is just a spherical accretion with compositional.
Right, the disk simulation is by Hopkins. Quite right, well pointed out. In fact, he uses a Shikurin-Yaev accretion disk, and he says the viscosity is not correctly accounted for. He doesn't think flickering needs to be that fast. It might be 10 million years, it might be 1 million years, but he'd be surprised if it was much shorter than that. And the range of variations would be much like these guys, 50 dBs, which, by the way, is down by 30 dBs, factor of 1,000, on what we observe, because we're quiescent at 10 to the minus 8, and we're saying it was at 10 to the minus 1 or 1 Eddington. So you need a lot more variation in practice than what you see in these models. But however, the idea is there, that these AGNs are flickering like crazy. And you probably know that the Kepler got a couple of Seyferts in its beam, and they flicker like crazy too, but you've only got a time frame of a year or two. So let me finish up by saying, there's a huge amount of activity going on at the Galactic Centre. I feel, like exoplanet science, that Sagittarius Star future-proofs astrophysics. I think we'll be doing this stuff forever. There's so much more to go after. There's so many amazing experiments which will just get better and better and better. You know, gravity on ESO, for example, is just one of a succession of 50 or more experiments you could list which are coming along down the pipe. I think this is one place we'll be working on for time immemorial, much like exoplanet science. In fact, what I'm showing you here is the VLBA network trained on Sagittarius Star. I think the goal there is this event horizon shadow experiment. So here are my final thoughts. I feel it's hard to escape the fact that the galaxy has experienced something very powerful on timescales of 10 million years or less. The Fermi bubbles alone, the X-ray bubbles, the UV, the X-ray emission in 07, 08, I can go on and on. There are lots of diagnostics which seem to be saying, I haven't even mentioned to you new observations of high-pressure cloud off the galactic plane, which are way overpressured with respect to their background, which is really interesting as well. So, of course, it's a front row seat to a very powerful event, which is why I say it's future-proofing astrophysics, because this is the best place to look for years to come. I believe the imprint of full-blown Seyfert activity is visible across the stream, both in terms of the emission, and also the UV absorption diagnostics being very hard. But, to be honest with you, the rapid variation of 80 dBs seems way too high to be consistent with modern models. Steve Balbus, however, said he feels the way to do this is to dump gas with MHD and have it collimate into much smaller footprints when it hits the disk, and that would give you a much more violent reaction. But the models can't do that at the present time. The HST observations, you're seeing many sight lines across the bubbles, and also the velocity gives you the front and back. And using halo stars, I think, is very inspired, as they're doing now. And so AGN bursts, frequent, short, and sharp, stochastic flicker noise behavior. And finally, it's clear to me now, more than it ever was before, that we need some kind of narrative for all of this, and these GRR MHD models are going to have to basically integrate their approach with the approach of the star formation modeling teams, as I showed before. Thank you very much.
So, thanks for this fantastic talk about the Galactic Centre, the controversies about the Fermi bubbles, and possible origin of what we see. Podium is open for questions. Please go ahead. I'll make more light. Matthias, wait.
I'm not sure how meaningful this question is, but I would expect radio emission from the same electron population that you attribute to the Fermi bubbles.
So, radio emission from what?
Radio emission from the same electron population in the galactic magnetic field.
So, the models I've seen, like I could find it by an Israeli physicist, not Zvi Paran, but a colleague of his.
Eli Waxman, probably.
Matt Hayes.
in his model is somewhat consistent with that.
So I was wondering about the correlation between the Planck signal and the Fermi bubble, if that might be remainder.
It's begins with G. Galactic or something like that is an Israeli physicist. I know he's worked with Steve Brown. So he has a paper about the Planck and the WMAP stuff.
All right.
And I just take their models on board from what they're.
Okay.
So from Matthias to Matthias.
I think they have to harden the electron population a bit to get it to work with.
So two questions. One, why cannot the Fermi bubbles be stationary states? And two, can we measure any proper motion associated with the Fermi bubbles?
I don't think the latter is possible. That's something that I don't know what I'm aware of. Why can't they be static?
Mm-hmm.
So,
like a steady state or just continuously outflowing and then...
Well, look, the idea of a fossil cavity where stuff has been blowing forever and ever, I think there is that has some legs actually. So there are, you see the puff, puff, puff of radio lobes where stuff is re-inflating through what's been before. NG33079, you have disk-wide wind, and you have a sort of an internal wind and something going off right in the center. So I don't doubt that things are reoccupying the same cells. But do you need to keep that going for billions of years? Why can't it just be on timescales of tens of millions of years? So in our annual reviews, we don't find any evidence on 10 kilopascal scales for winds older than 10 million years. But I can imagine that if you re-evacuate something, that could be a signal of something older, a fossil. But that's very different from the idea of something which is a billion years old.
So our guest from California.
A big part of your argument was the H-alpha emission from the Magellanic Stream. My understanding is that the galactic radiation field, which you were saying is not strong enough to produce that emission, is relatively uncertain. It's essentially the escape of ionizing photons from the disk or from H2 regions O stars. Can you convince us that that is really known to a factor of 3?
Oh my gosh, I wish Chris McKee was here. He would love you. He has been my nemesis. I first put a paper out. I made a small slip on my assumptions. He said, you've got too much coming out. It's no more than 1%. And Pierre Maddow wrote a document, and it had McKee versus me, and the winner would win a prize or something. And that was 25 years ago, and he's been batting with me ever since. And he says my numbers are too high. He says, if anything, no galactic radiation field has an escape fraction higher than a few percent. Actually, that's been known for many galaxies.
But where does that come from?
So
we have a really hard time figuring out the escape fraction of galaxies that are distant. This is why I'm asking you. It's not something we can just easily predict, but I presume in the Milky Way you can measure it.
All right, so high redshift is relatively easy, and they don't get numbers higher than 10-15%. And those numbers were brought down by subsequent. Steidel's first paper, I think, were too high. They were halved by other groups that followed. Low redshift, it's even been done with various UV absorption diagnostics with dependent opacity, work by people like Heckman, Leiderer, I can't remember all the authors, and they get numbers between 2 and 8%. So there was one paper which put the escape fraction up at sort of 20 or 30%, but they forgot to correct the galactic absorption, because that generates lots of band edges and fine lines, which you have to remove from the spectroscopy. So I think I'm happy to result of this, and if you find evidence to the contrary, I don't think you will believe that UV escapes from normal galaxies can be higher than 10%.
Well, here it needs to only escape 10 gauge or 50 gauge escape gas.
Yeah, and I've already shown you that escape fraction there is 6%. That's already quite high. And by the way, the stream is thought to be more like 75 to 100 kiloparsecs, so that would be even harder to achieve. And then Chris McKee gets in my cases, it's still too high. He thinks it's even lower than that, because he says, take that's right. He says, if you ask the question, what is the covering fraction of 10 to the 17 H1? He says, across the whole sky, it's close to 80%. At 10 to the 17, you absorb UV, and that's, I know at the Galactic Centre, not somewhere else. So he says, that argues that it should be even less, or so much less. You're only measuring things for the local, not further out. So anyway, it's been a long-standing battle between a lot of groups.
So, next question, all the way up here, Baska.
So in the last slide where you showed the simulations and the flickering accretion, so I see that the F Eddington goes up to 10, so that's 1. However, the idea of this ancient cavities, right, the Fermi bubbles. Would that be aided further if you were to relax that assumption of F Eddington equals 1 at very early times? Like if you assume that the black hole was super Eddington very, very initially, let's say between 10 to 12 gigayears ago, and then how would that power spectrum look like today?
Yeah, it's funny you should say that. In my talk at Harvard, Ramesh Narayan made a similar comment about Eddington, super Eddington models. And yeah, if you go there, it eases everything. But it's very hard. You know, things get much more pointed. They're not no longer wide and diffuse. You don't get winds. They're more like collimated structures. But I don't know what the strongest case is for super Eddington anything. I mean, maybe one day this will be obvious, but at the present time it's extremely controversial to say super Eddington. So if you know a strong case for saying that these things can exist, then I'd be very impressed to hear it.
I mean, there is theoretical advances in understanding super Eddington accretion because it's not really a hard limit in the sense of accretion. You don't.
Yeah.
So.
Narayan's point was the same. You know, this should be more common and more obvious than we observe.
Because the energy doesn't scale as n and it becomes log n. So it's not such a big, how do you say, exceeding the fundamental limit. It's not. It actually changes the scale.
Yeah, I buy all of that. And it would be wonderful one day when we get a lot more diagnostics, if we see the hardness of the spectrum, which it must be, to go super Eddington, go up as we approach the center of the cone, and then go down again. Imagine that, you saw the footprint of super Eddington on the screen, because you get soft diagnostics are broad, hard diagnostics give you smaller cones, and the hardest diagnostics like FE 10, 14 give you this tiny forward-centered radiation.
Diagnostic, but also the life cycle or the duty cycle of AGN activity.
Yeah, so I can imagine if we have a lot more, there's a lot of diagnostics already coming out, but I can imagine one day we have many more because we've got bigger telescopes coming, and we'll see the imprint of different cones of hardness, and super Eddington becomes the most centered cone.
So let me also intersect a question. I have seen you, sorry. How quickly would these bubbles go away? The background of my question is when we model the flow of motion in the central molecular zone, we see a flickering of order of 10 to 15 million years, where gas sloshes back and forth from the left side to the right side. We see that the central molecular zone is highly anisotropic. All the gas is on the left-hand side, all the young stars is on the right-hand side. And we would expect some of this flickering to kind of be transported inwards and have a time-steady accretion flow towards the galactic center. So if a similar thing happened, let's say, 30 million years ago, would you see evidence of that?
Yes. In fact, I failed to mention, like so much else I've just left out, shorter, is you convolve these outputs with those sorts of timescales. It's much more like what Phil Hopkins is thinking in terms of viscosity. You get like one every 10, 20 million years, in principle, maybe 10 to 30 million years. You get, I forgot to mention, the AGN models are pushing now up to an Eddington of 1, not 10% like we did. They're saying it has to be more, and they can be as often as once every 10 to 20 million years.
But are you saying you can exclude it because you would see then another bubble further out that is fading away?
So these are relic radio structures. These are seen in external galaxies, but not so far in the Milky Way. And maybe it's there, we just haven't found it.
Okay, so it would be very faint.
Yeah. So as we see it today, it's our graph, I think it would fade within 10 million years to the level of undetection.
Could you give some comments about detection of the Fermi bubbles in Planck data?
In
Planck data.
what data?
Data.
Planck data?
Yes.
I'm sorry, I'm just not up on that. I meant to get to it, but I've been so busy with being a director, a boring director. I've got the papers in a little folder. I know you see this stuff in that late stuff, but I don't know what we're inferring from it yet. I'm looking forward to reading it.
So I see no further hands up. We thank Jos again.